Good morning, good afternoon, and good evening, everybody. I am Stratos Davlos, CTO at Innoplexus, and it's an honor to join the NVIDIA 2020 Global Conference. Today, I would like to present some of the work that we do at Innoplexus. We are a small, agile startup in artificial intelligence and bioinformatics. In the drug discovery space, it's very expensive to produce a drug, and that's very well known. There's a law called the E-Rooms law, and according to that law, the cost of drug discovery doubles every 9 years. So if you were to take $1 billion in 1970, and you would produce about 10 new drugs. And if you try to do that today, you can barely produce half a drug. So the cost of drug discovery is very expensive. And that is kind of interesting because the number of publications and data available in the bioinformatics space follows an exponential curve. So you have a lot of data out there. Most of it was generated the last 2 years. And if you were to continue to do business as usual, then there's a significant gap that you create between your understanding of the world and how the world evolves. At the same time, in the computing industry, we enjoy Moore's law, so the computing speed doubles every 2 years. So if you take data plus compute power, that's the perfect proposition to use AI. And with AI, you can change the ability to do drug discovery from a flat, linear improvement to an exponential improvement. And that follows the scientific data proliferation curve. So that's the business we're in. Today, I'll talk a little bit more about small molecules, and because small molecules are huge. They play a significant role in developing new therapeutic agents. They're also used to probe biological functions, and they can be used also to inhibit a particular function of a protein. So a protein that is responsible for the viral spread of COVID-19 can be inhibited with the right molecule, and it can also disrupt any protein-to-protein interaction. So to create a small molecule, it's fairly expensive. It takes about $260 million, I'm told, and it takes 3 years. And a small molecule, just like any other molecule, needs to satisfy several physiochemical and biochemical criteria so there can be a good potential to become a drug. So there is a solution, there's a need for a solution, and this is where we stepped in, that will automate the whole process of generating good molecules to inhibit a particular behavior. So that solution comprehensively scans the chemical space and really enable us to generate a new hypothesis of a viable molecular structure that is a very good candidate for drugs. So we used deep learning, and I'll get into more detail specifically into the technology we used, and of course partner with NVIDIA. And so we run all that deep learning algorithm on NVIDIA V100. And part of our algorithms also automatically got prioritized through NVIDIA hardware based on their binding affinity, their drug-like properties, and ADMET properties, and many others. All right, so at the very high level, we analyzed a lot of data. And we extracted entities and the relationship between those entities and prepare them in a way that we could, do some biological filtering and then use them to train our neural networks. And what you can see here is an encoder-decoder system that was paired with reinforced learning. That system could generate good molecules, could generate millions of them, and the goal is to get to a handful of those. So through subsequent tests, we managed to get to 5 molecules for COVID-19 that are extremely good candidates, and they're moving to the next stage. The molecules we generate typically have a very, very good affinity score, and when you look at the bullseye characteristics of them, they're almost perfect. So let's see how that was done. We use a lot of public data sets as well as internal data sets that are available at Innoplexus. Innoplexus has been accumulating data over the last 5 years or so. We use our biologists to augment the data sets and taxonomize them in a way that can be very useful. So we used, for example, from zinc, a couple million synthesizable molecules. For Chembil, we just took, specifically to 3CL Pro, which is the target protein for COVID-19. We took the protease inhibitors and also took other classes of enzymes because we want to make sure that the system eliminates properties that are undesirable. We took into account a lot of three-dimensional structures that exist in the protein data bank and a lot of patents and literature, molecules that appear in literature to make sure that the molecules are novel. So after we created our data, then we trained a variational auto-encoder that had a series of learning objectives. The first one was we wanted to make sure that the system learns the rules of nature, both chemical and structural. We wanted to make sure the system learns the information about the target protein and the specific binding cavity characteristics of that protein. I want to make sure that the system learns what's desirable and what's undesirable as a molecule and how to prioritize things. So the variational auto-encoder was chosen amongst many other technologies that can synthesize molecules. And we chose it because we wanted to use TTLP, the tensor train induced learnable prior. The combination of TTLP with variational autoencoders allowed us to encode the SMILES, which is the chemical notations of a molecule, and other properties in the latent space. So this was a learnable prior that was used to effectively compute the conditional probability and the marginal probability. And with this distribution, we could compute the likelihood of an unlabeled data to belong to the distribution by marginalizing out the unobserved conditions. So a lot more detail on this in the technical session. But for now, I can tell you that when you pair this capability with an adversarial network that has a reward system, then you get into a solution where the system improves its output over time by better understanding what's a good molecule and what not. So the reward system, there's a function here that comes from 3 self-organizing maps. And those were, a map that showed general protease information, a map that mapped out 3CL Pro protease information, and also a map that told us how old the molecule was if it existed in a patent. The evaluation of the molecule was very, very encouraging, and here's all the different tests that we took it through. So the target protein binding potential was extremely important, and its corresponding affinity score, specifically to COVID-19. We worked on the 3CL Pro protein. ADMET properties were extremely important as well. So the absorption, distribution, metabolism, exertion, and toxicity were evaluated. So all molecules passed that test. Any empirical rules were also evaluated, and other things like, we penalize molecules for the corresponding ring size and many other filters. All right, so in terms of technology, we use PyTorch, and then we use NVIDIA Teslas to the NVIDIA GPUs to create our machine learning pipeline. For the data preparation, both pre and post processing, we exploited NVIDIA Rapids. So the data frames, the Q data frames, were extremely valuable. And we use about 8 NVIDIA Tesla V10s, and the reason I'm saying about is because depending on the task, we use a different number of GPUs. The next slide actually gives you a little bit more understanding of the different tasks and how long they took. So for example, the longest pole in the tent was the understanding of the three-dimensional structures and how we can fit a molecule and its structure into the cavity itself. So to run just 100 epochs, it took us 32 hours and 8 GPUs. There are some huge benefits using GPUs over CPUs. We were like 30 times faster to generate the sums. We're about 10 times faster to get a batch of 300,000 molecules and generate those. So that was a huge ingredient for our success, the partnership with NVIDIA. The other huge ingredient for success was our team of superheroes. We had a very small and agile team. Everybody was passionate about what they were doing. Ashwin Rathod, great, huge thanks to Ashwin and his leadership and passion for novel molecule generation. Vivek Singh, not just a data scientist, but also he has a deep biological background, so he's rare species in my book. Vibash was outstanding and coding the whole system and figuring out complex solutions, simple solutions, complex problems. Rohit was invaluable in helping us understanding the validity of the output of the algorithm. So thank you very much to the team. This is our card. We would welcome anyone who would like to get in touch with us to either look at our portfolio of AI capabilities as well as the work that we've done in novel molecules. So with that said, I want to thank you everybody for your attention and open it up for questions.